Good afternoon, boys and girls. Welcome to another lesson on Technical Sciences, grade 12. It is Saturday, the weather is beautiful on the outside. I hope that yours is actually the same and that you are really having a good day. Now, my dear learners, today is our question and answer session, and we are continuing with electromagnetic radiation. In other words, for today, we are only going to focus on questions and answers and how you need to prepare for the examination for this section of the work. So I was really hoping that I would get more questions that you want me to deal with as per the examination guidelines, but I did not get some. Not a problem at all. What we'll definitely deal with is the questions that I have prepared for you. And they are questions from previous examination papers. So they are definitely well standardized and they are going to prepare you thoroughly for your final examination. So I hope you have your pens and paper ready or your notebook so that we can start with the lesson for today. So the structure of the lesson today, my dear learners, we will have an overview and quickly remind ourselves what the examination guidelines expect us to know in this particular topic. And then in the features of the topic, we will be learning electromagnetic radiation, but through doing questions altogether, because it's definitely a question and answer session. And then I will give you more tips about exam preparation as well as mark allocation. Now, because we might be having new learners that are joining us today, please note that this topic on electromagnetic radiation is paper 2 altogether. It is paper 2. So make sure that you prepare for it when you prepare for your paper 2 examination on technical sciences. So this is what we are required to know as per the examination guidelines. Firstly, we are required to be able to define the term electromagnetic wave. And I told you that sometimes we might not say electromagnetic wave, we could actually say to you electromagnetic radiation. And this is a changing magnetic and electric field mutually perpendicular to each other and the direction of propagation of the wave. So always remember there, we will give you 2 marks or nothing for this particular definition. So you definitely have to know everything. And then we must be able to discuss properties of electromagnetic waves. And I have taught you 4 of those properties, and I'm sure you know them by now altogether. The first one you will recall, we talk about the fact that they are transverse waves and can be polarized. The second property that we discussed was that they obey the wave equation. The third property that we looked at was that they travel at a speed of 3 × 10⁸ meters per second in a vacuum. And the last one was that they are self-propagating in that they do not require any medium to move. So at least know those 4 properties. We can ask you at most to give us 4 of those properties. And then use this equation, C is equal to frequency multiplied by wavelength, to solve problems involving speed, frequency, and wavelength of light. Furthermore, remember, you can also use this formula where we say speed is equal to frequency multiplied by wavelength, where your speed is represented by the letter V. So this one is actually the best equation to use because you can substitute the speed, whether it's moving in a vacuum or whether it's moving in a given medium altogether. So you can use this particular equation. And then we must be able to discuss electromagnetic spectrum in terms of frequency as well as wavelength. Even more, we know that we must be able to discuss it again in terms of energy. So what does this tell us, my dear learners? It tells us that we need to remember the relationship between frequency and wavelength as well as energy. And without really going deep, let us just quickly check from our memory what we recall. And you will know that the higher the frequency of an electromagnetic wave, the shorter the wavelength and the higher the energy. So high frequency corresponds to a shorter wavelength, but because the frequency is high, it corresponds to a higher amount of energy that is carried by the photons of that electromagnetic wave. And then we have the wavelength. Now with the wavelength, my dear learners, we know it is actually that distance between two successive points that are in phase. Now, another relationship there is that we know when the frequency is low, then the wavelength is going to be longer and the energy is going to be less. So a higher frequency, rather a lower frequency, corresponds to a longer wavelength. But again, because the frequency is low, then the energy that is carried by that electromagnetic wave, I also expect it to be less altogether. So that is the relationship. And furthermore, we are required to know, or rather to be able to arrange the electromagnetic spectrum in order of increasing frequency or decreasing frequency, or increasing wavelength or decreasing wavelength. So this is what we need to know altogether. So we then check and say, but we know all the types of electromagnetic waves that make up this electromagnetic spectrum. And we know that we have gamma rays, we have X-rays, we have ultraviolet radiation, we have visible light, we have infrared, we have microwaves, and we have radio waves. And we know the order that I have given you. If you go from gamma rays all the way to radio waves, you are going in the direction where the frequency is decreasing. In other words, gamma rays have the highest frequency, and when you go to X-rays, then microwaves, then rather when you go to X-rays, then ultraviolet radiation, then visible light, then infrared, then microwaves, then radio waves. In that order, we are going from a higher frequency to a lower frequency. In other words, gamma rays have the highest frequency and it keeps on decreasing up until you go to radio waves. in terms of wavelength, from gamma rays to radio waves, it tells me that the gamma rays have the shortest wavelength and the radio waves have the longest wavelength. Therefore, going from gamma rays to radio waves, it means the wavelength is increasing because our gamma rays, they have the shortest wavelength and our radio waves have the longest wavelength. So again, from gamma rays to radio waves, the wavelength is increasing. Then in terms of energy, we know that gamma rays have the highest frequency and radio waves have the lowest frequency. And we know that the higher the frequency, the higher the energy. The lower the frequency, the lower the energy. Now, if gamma rays have the highest frequency, it means they are going to have the highest amount of energy carried by that electromagnetic wave. And then in terms of radio waves, because they have the lowest frequency, it means the electromagnetic waves, they carry the lowest amount of energy. And therefore, because gamma rays have the highest frequency and the highest energy, and radio waves have the lowest frequency and the lowest energy, it means that going from gamma rays all the way to radio waves, it means the energy of the electromagnetic wave is decreasing. So remember that. Then we must also be able to state uses of electromagnetic radiation, what we use electromagnetic waves for. And these electromagnetic waves within the electromagnetic spectrum, they are different and they have different uses. And we have discussed those. And what we will be doing in these questions today is that we'll be looking at more of these uses that, you know, the question is also informing us of. But we will also then answer questions that require us to give the uses of these electromagnetic waves or electromagnetic radiation. And we know again, my dear learners, with a couple of these electromagnetic waves, we must then know which ones are really dangerous and what are their disadvantages. For example, when you talk about your gamma rays and so on and your ultraviolet, we need to know some of the disadvantages. Then another definition that we must know is the definition of a photon. And we know the definition is very simple. It's a quantum of energy, 2 marks. All these keywords, they must be there. And why do we say it is a quantum of energy? Because that is how we quantify the amount of energy that is carried by an electromagnetic wave. It is through the photons, the little packets of energy that the electromagnetic waves have. And then we must be able to use the equation E is equal to HF to do calculations involving energy, frequency, and wavelength of light or any electromagnetic wave. And we definitely know that, my dear learners, this energy is directly proportional to the frequency. Why can we say the energy carried by that electromagnetic wave is directly proportional to the frequency? Because H is a constant. In other words, the higher the frequency of an electromagnetic wave, the higher the frequency of the electromagnetic wave, the higher the energy that it carries. And the lower the frequency of an electromagnetic wave, the lower the amount of energy it carries altogether. Right, and we know that H is a constant. It's a Planck's constant, there it is, and we are going to get it from our data sheet, so we don't need to remember the value of from our head. It will be there from our data sheet on table number 1. Again, my dear learners, remember, sometimes you might not be given the frequency and you could be given the wavelength, and you'd be required to actually calculate the energy carried by an electromagnetic wave. So if you have the wavelength, then the easiest way to really work with that question to calculate the energy is to use this second equation that says E is equal to H multiplied by C divided by lambda. In other words, the energy carried by the photons, it's equal to the Planck's constant multiplied by the speed of the electromagnetic wave in a vacuum divided by lambda, which is the wavelength altogether. And all these two formulas, they can help you to calculate the energy. And this is really the shortest way of calculating the energy carried by a photon if you're given the wavelength. Like I have told you before, you could still use this formula, E is equal to HF, but it will be a multi-step, so you'll have to calculate the energy in 2 steps. So we'd rather avoid that and use only a single equation. Right. Then we get to the next one. From our question paper, we will be having a formula sheet, and from our formula sheet, these are the formulae that you need to expect. These ones from table 2. V is equal to F multiplied by lambda. E is equal to HF, or E is equal to HC divided by the wavelength. And also T is equal to 1 over F. These formulas, you will definitely know that they are relevant. And what is going to tell you that they are relevant? Because you will see that we are dealing with waves. So these are the formulas that you need to use. And we know that the V in this formula stands for the speed, the F for the frequency, the lambda for the wavelength. In the second formula, this one, the E stands for the energy, the H stands for the Planck's constant, the F stands for the frequency altogether. On this one, still the formula to calculate the energy that is carried by the photons, and there the E is for that energy, the H is the Planck's constant, the C is the speed of electromagnetic waves in a vacuum, and the lambda sign represents the wavelength. Then on this formula, T is equal to 1 over F. We know the T represents the period, and there we have 1, and the F there represents the frequency altogether. Right, so we get straight to the questions. So we are learning electromagnetic radiation. Right, now we are given a diagram there, and they tell us the diagram below shows the spectrum obtained during the dispersion of white light. So there we have white light that has actually dispersed. Now, when white light disperses, it simply means That is when it is breaking into its component colors. So if they are telling us that white light has dispersed there, it means white light has been dispersed into its component colors. It has been broken into its component colors. And therefore, all these 7 colors, including X, are all the colors that white light breaks into during dispersion. Right, gives us 7 colors. Then we are required to define the term dispersion. So we can see if we have white light and it disperses, this is exactly what it's doing. It is breaking up into its component colors. So dispersion is the process whereby white light breaks, rather it's a phenomenon. Let's put it nicely there. Right, as per your examination guidelines, let's write it nicely there for you. There we go. We say it is a phenomenon. Phenomenon. It's a phenomenon whereby white light breaks into its component colors. And this definition you must know, you will actually get it under the section on light. Right, so it's a phenomenon whereby white light breaks into its component colors. So that is what we refer to as dispersion. And everything must be there, all the keywords, and they must be used in the correct context in order for you to obtain all the marks altogether. Then we are required to write down the name of the color of light represented by X. Now, there we've been given violet, we've been given indigo, and we don't know what X is. Then we have green, yellow, orange, and red. Now, my dear learners, you will recall that, and you know, we've been taught this quite a number of times, even in our primary school years, to remember the 7 colors that white light actually produces, or the one that white light breaks up into. And we remember it as Roig beef. It is remembered as Roig beef. And we know the R stands for red, the O for orange, the Y for yellow, the G for green, and therefore it means the one that will follow there, which is X, must definitely be blue. So this one will be blue, the I is for the indigo, the V is for the violet altogether. So we have red, orange, yellow, green, blue. So the color of light that is represented by X, it is definitely blue. So you need to remember that, my dear learners, that the 7 colors that white light breaks up into during dispersion, it's definitely 7 colors that we remember by that with the Roig beave. And then you must know what each letter represents there. All together. Right. Then we are being asked which color of light has the highest frequency. Now, out of all these 7 lights, we must know which one has the highest frequency. Now, if I ask you what actually comes before violet, a learner will say to me, Menier, it is definitely ultraviolet. And then if I ask a learner again, what comes next to red, then the learner will say, Menier, it is definitely infrared altogether. Now, what do we know? We know that ultraviolet is here, it has the highest frequency. If infrared is there, we know infrared has a lower frequency. So it means now I am using this tip to see that, because there I can say, okay, next to violet, I have ultraviolet. Next to red, I have infrared. That tip already teaches me to say, okay, it means if I go from ultraviolet, it has a high frequency, and I go to infrared, it has a low frequency. It means my frequency is definitely decreasing as I move to the right, as I move from ultraviolet to infrared. Or to put it in the context of this question, it then means that because when I'm going to the right, the frequency is decreasing, it means the type of light that is on the left must be the one with the highest frequency, and the type of light that is on the left, rather on the right, must be the one with the lowest frequency. So what does this tell us again? It tells me that violet then must be having the highest frequency, and then the red must be having the lowest frequency. So our answer there is simply going to be violet altogether, and that is going to give us a mark. Then we are given more questions here. It reads as follows. A photon of a light wave has 7,0 multiplied by 10 to the power of -19 joules of energy. So here, my dear learners, we've been given a photon, and that photon has energy in it, and the energy that is within that photon, it's 7,0 multiplied by 10 to the power of -19 joules. Then we are required to define the term photon. And by now we know this definition, my dear learners, altogether. It's a quantum of energy, simply like that, and it's 2 marks. So quickly to just check it there, a photon, we said it's a quantum of energy, and that will be 2 marks altogether. Good. Then we are required to calculate the wavelength of the wave. So if I want to calculate the wavelength of the wave, and I can see that I've been given the energy that is carried by the photons of that wave, it means I know the value of E altogether. So I've been given the value of E. What I also know is that I have a value of H, which is a constant. I have a value of C, which is also a constant. So I have the energy of the photon, I have H, which is the Planck's constant, and I have C, which is the speed of electromagnetic waves in a vacuum. So I can definitely see if there's any formula that can give me a relationship between E, H, and C, which are the values that I have, versus what I need to calculate, which is then the wavelength. Then I will say, okay, let's go to my formula sheet and look under waves, sound, and light. And I can definitely see that the formula that will be more relevant is this formula, because I have the value of E, I have H, I have C, and I am left to calculate whatever that they have asked me. Are we clear? Then I will say, that E, which is the energy, is equal to Hc divided by the wavelength. And then for the H, I know my H is 6,63 multiplied by 10 to the power of negative 34 altogether. And then I will multiply that by the value of C, which is 3,0 multiplied by 10 to the power of 8 meters per second. And I will divide this by the wavelength, which is what I am looking for. Then to calculate the wavelength, I will then check there. Remember, we have a value for E, and our E, we agreed that it is 7,0 multiplied by 10 to the power of negative 19. There it is given. So I substituted the value of E, I substituted the value of H, I substituted the value of C. And remember, where did I get the value of H? There it is. I get it from the data sheet, and it is that value. Where did I get the value of C? There it is. And it is also a constant value. Then we go to our calculator. Right, let us perform our calculation there. So to make this easy for you, let's start it this way. Right, so we will leave this one, this side, the value of E. Seven comma 0 multiplied by 10 to the power of negative 19. Then I work out the right-hand side. The right-hand side, I'm going to take 6.63 times 10 to the power of negative 34. I will multiply it by 3,0 multiplied by 10 to the power of 8. Good. And then all of that is going to be divided by the wavelength altogether. Right? So this is going to give me 1,989 times 10 to the power of negative 28. And I will divide that by the wavelength altogether. So I started to work with this part first, where I took the H and I multiplied by the value of C. Then we do our mathematics. The lambda must now cross multiply to the left. So I will have 7,0 multiplied by 10 to the power of negative 19 multiplied by the lambda. And this is going to give us 1989. And I will multiply that by the 10 to the power of negative 28. Then if I want the wavelength, it means I must divide both sides with 7,0 times 10 to the power of negative 19. And that will divide and give us 1. And then whatever I do on the left-hand side, I must also be able to do it on the right-hand side. Then it means this side, which is the right-hand side, I must also divide by 7,0 multiplied by 10 to the power of negative 19. So this will be then we say 1989 multiplied by 10 to the power of negative 28. And I will divide that by 7,0 multiplied by 10 to the power of negative 19. And I find my answer there to be giving me 2,84, and I will take that to be 2,84 multiplied by 10 to the negative 1, 2, 3, 4, 5, 6, 7. And this will be minus 7. And remember, we are calculating wavelength, so our answer there must definitely be in meters. Right, so our answer there is definitely 2,84 multiplied by 10 to the power of negative 7. And our answer there is going to be in meters. Definitely 1 mark there for the formula, 1 mark there for the substitution of energy, 1 mark for one substitution there, 1 mark for another correct substitution, and 1 mark for the final answer that is carrying the correct units. If it doesn't have any units, then we are not going to give you any marks for the final answer. And then we go to 9.2. They said to us, an electromagnetic wave is defined below. Write down the missing word. Then the definition says, an electromagnetic wave is a changing, and we want to fill in something there. And we'll check what that is, but it's a changing something, and it's a type of a field. And a changing magnetic field mutually perpendicular to each other and the direction of propagation of the wave. So what changes? We know it's electric field as well as the magnetic field. But in this case, they told us about the magnetic field. In other words, there, the type of field that must be existing is electric field. And you don't write a lot. We just wanted the word that is missing. So that word there, electric, is the only one that is missing. Because when we define electromagnetic wave, we define it as a changing magnetic and electric fields that are mutually perpendicular to each other and to the direction of propagation of the wave. Are we together? So we were just looking for the word electric. Then we move to question 9.3. Now, in question 9.3, they tell us 4 of the 7 electromagnetic radiation are listed below. So they gave us ultraviolet rays, microwaves, visible light, as well as infrared rays. Then we can definitely ask ourselves which ones have been omitted, because this is a learning process. Are we together? So we can definitely see that the gamma rays are not there. We can definitely see that the X-rays are not there. We can also see that radio waves are not there. Are we together? So when you are studying, my dear learners, because you won't be getting the same question as the ones that we are doing, use the questions to learn. Ask yourself questions. So the first question that we asked ourselves is that which of these electromagnetic waves have actually been omitted? All together. Right. Then we are then required to write down the name of electromagnetic radiation from the list given above that, firstly, is used in night vision devices. Now, night vision devices, my dear learners, please note that they use infrared radiation. Are we together? They use infrared radiation. Right, and I wouldn't want to go into much details about it, but it has to do with infrared, is actually able to create an image at night of any object that is around altogether, and it uses heat to do that. The heat that is emitted by a particular living thing and so on. As a result, because of the heat that is being emitted and the nature of infrared radiation, then you will see that infrared radiation is able to detect some of the heat that is produced, and you are able to then create a particular idea about the object that is around you at night. That is obviously if you are the one that is using the night vision device. Then the one that leads to skin damage when one is overexposed to sunlight. So we have 2 keywords there, and one of the critical words there is sunlight altogether. And we definitely know the type of electromagnetic radiation that we associate with sunlight is ultraviolet. So what does this mean for us? It tells me that ultraviolet radiation, we get it from the sun. That is something that we need to know. And it also tells me that being overly exposed to that ultraviolet radiation is going to cause skin damage. Even worse, it may result in skin cancer altogether. So remember that being overexposed to sunlight definitely can lead to skin cancer or skin damage. Then we are looking for the type of electromagnetic radiation that has the lowest energy. And the one that will have the lowest energy must be the one that has the lowest frequency, right? Because you know the relationship between frequency and energy. Furthermore, my dear learners, the one with the lowest frequency must actually be the one with the longest wavelength altogether. Out of all these four, remember, we are still dealing with the list that is given above here. So even though we know there are radio waves, and radio waves actually have the longest wavelength, but we are not interested in that because it has not been listed there. So we only talk about those that have been listed, because these are some of the mistakes that you will find yourselves and learners to be committing, because you will be knowing that the radio waves have the lowest frequency, they have the longest wavelength, but they have the lowest energy. And you find that Elena talks about that. But remember, we've been given an instruction to actually work with those that are given on the list. So we must look from the list, which one has the lowest frequency, which one has the longest wavelength, and therefore we will be able to find which one has the lowest energy. And the one with the longest wavelength here, we definitely know that it is microwaves. Altogether, they are just before the radio waves. So our answer there is definitely microwaves. They are the ones with the lowest energy because they have the lowest frequency altogether. So they will have the lowest energy. Or from these four, microwaves are the ones with the longest wavelength. So they will have the smallest amount of energy, or what we refer to as the lowest energy. Right. Then we are required to name 3 electromagnetic radiations not shown in the list given in question 9.3 above. So we must give the names of all the electromagnetic waves that have not been shown altogether. And we definitely know that gamma rays have not been shown. Secondly, we know that X-rays have not been included. And we also know that radio waves have not been included. Are we together? Good. So that marks the end of that question, and it is 18 marks. I think this was the easiest question altogether, and you could have got all the marks. So really, my dear learners, prepare thoroughly for this section. Can you see the marks that you can actually obtain here and actually do well altogether? Good. Then we are given a question there, and it reads as follows. The types of electromagnetic radiation are arranged according to frequency in the table below. So there we have the type of electromagnetic radiation, or the type of radiation, and we have the frequency. Now, before we even go to the questions, we can actually check with the frequencies what is happening here. Now, my dear learners, we can definitely see that the radio waves have a frequency between 10 to the power of 5 hertz to 10 to the power of 10 hertz. And microwaves 10 to the power of 10 hertz to 10 to the power of 11 hertz. So within that range of frequency, that is where you get your microwaves. And we can definitely see that as we go down from radio waves up until gamma rays, we can definitely see that, my dear learners, the gamma rays their frequency begins at somewhere around 10 to the power of 18 hertz. So that is the one with the highest frequency. So from this table, my dear learners, we can definitely say from radio waves up to gamma rays in that order, which is very much correct, from radio waves to microwaves to infrared to visible light to ultraviolet to X-rays as well as gamma rays. The frequency is definitely increasing altogether. But what do we know about the wavelength? When you go from radio waves up until gamma rays, it means you are starting with radio waves that have the longest wavelength, and then you get to gamma rays that have the shortest wavelength. So it means the wavelength is decreasing when you go from radio waves all the way to gamma rays. Then in question 8.1, you are being asked, how are electromagnetic waves generated? Now, I told you, my dear learners, that electromagnetic waves are generated due to charges accelerating, and that is 1 mark. It is because of charges that are accelerating. And you'll remember I told you that for you to have that electromagnetic wave, you must have charges of that electromagnetic wave accelerating. In that, there will then be a changing magnetic and electric field, and a wave is also going to be propagated, and you will have that electromagnetic wave being generated. So you will have an acceleration of charges, which then gives you that magnetic and electric fields, which are also perpendicular to each other, but as well perpendicular to the direction in which the wave is being propagated. Then you are asked, what type of electromagnetic radiation has the highest energy? Remember, energy is directly proportional to frequency. So the higher the frequency, the higher the energy. The lower the frequency, the lower the energy altogether. So we check, we say, okay, this then means because gamma rays, the frequency is 10 to the power of 18, and the others, the frequency is less than 10 to the power of 18. We know 10 to the power of 18 is a big number, all the way up to 10 to the power of 21. So the frequency is the highest on gamma rays, and because it is the highest on gamma rays, it then means the energy is going to be the highest. So our answer there must be gamma rays. And then we are being asked to explain the answer to question 8.2. So the answer there is very simple. Why did you say gamma rays have the highest energy? It is because gamma rays have the highest frequency. It is definitely because gamma rays have the highest frequency. Right. Now, that is reason enough. If it were me, I would really go further, where I try to tell them that by saying gamma rays have the highest frequency, it means the higher the frequency, the higher the energy. The higher the frequency, the higher the energy. The higher the frequency, the higher the energy. Altogether. Or another learner could have also indicated there after saying it is because gamma rays have the highest frequency, then another learner could have added there and said it is because frequency and energy of the photon are directly proportional to each other. Right, so that will be that in terms of question 8.3. Then 8.4, they tell us a certain type of electromagnetic radiation has a wavelength of 600 multiplied by 10 to the power of negative 10 meters. Then you are required to then identify the type of electromagnetic radiation by performing a calculation. Now, my dear learners, here it's a favor for them to tell you that you need to identify it by performing a calculation. I mean, if I want to identify a particular electromagnetic radiation, I can then check that, okay, there I've been given the types of radiation and there I've been given the frequency. So if I wanted to find out what type of electromagnetic radiation am I dealing with, then the best thing to do is to go and calculate the frequency. After you have the frequency, you will check in which range is that frequency. And then if the range is maybe between 10 to the power of 16 hertz and 10 to the power of 18 hertz, then I would say then I am dealing with X-rays. If I calculate frequency and I see that the frequency is between 10 to the power of 5 and 10 to the power of 10 hertz, then I would say, okay, I'm dealing with radio waves. So the only way that you will be able to identify which type of electromagnetic wave that is by doing what? By calculating the frequency and checking that frequency corresponds to which type of electromagnetic radiation. So I want to give you 4 minutes and I want you to calculate now by yourself the frequency. So the guidance that I'm giving you is that calculate the frequency of this electromagnetic radiation if you have been given the wavelength. So this value is the value of lambda, is the wavelength. So given the wavelength, I am asking that you calculate now the frequency of this electromagnetic wave. After you have it, then we are going to check which type of radiation does it correspond with. Right, so you have exactly 5 minutes for that. I really want you to test yourself and see if you are able to do these things. Right, so your 5 minutes then begins now. So remember, you first go and check your formula sheet and your data sheet. Formula sheet for the correct formula, data sheet is definitely for the constants, the values that are constant, right? We have 4 minutes to go. far more than what you needed. Right, my dear learners, really, as an exercise for yourself, do this type of questions and practice on your own, right? So to perform this calculation now, I need to go and actually just convert this value of the frequency of the wavelength, and I need to convert it to frequency. So how can I go about that? I can go to this equation that says V is equal to F multiplied by lambda. In other words, the speed is equal to the frequency multiplied by the wavelength. Good. There is my formula. I will get the first mark. Then I'm looking for V. Now, here it's a certain type of electromagnetic radiation. In other words, I can go back to my data sheet and actually just then check that the speed of the electromagnetic waves in a vacuum, it's that. So where I see a value, where I see the letter V, I know that I am talking about the speed. Although there it is indicated as C, you can also use it here because that C is the speed. So you can use it as a value for V. And there you will substitute 3,0 multiplied by 10 to the power of 8. And this is equal to the frequency, which is what you are looking for, multiplied by the wavelength. And the wavelength there is already in meters, so we are happy with that. We will put 600 multiplied by 10 to the power of negative 10. Right? And therefore, to get the frequency means that I have to divide both sides by 600 multiplied by 10 to the power of negative 10. And then it means this side I will be left with F. And then this side, remember, if I divide it by 600 times 10 to the negative 10, on the right-hand side, I have to do the same on the left-hand side. So I will divide both sides by 600 times 10 to the negative 10. Then to calculate this one, let us go to our calculator. We are going to say 3,0 multiplied by 10 to the power of 8. And I'm going to divide that by then the frequency will be 5 multiplied by 10 to the power of 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So it's 5 multiplied by 10 to the power of 15 hertz. So that is going to be your frequency. So I just did it twice to double check that my calculation there is 100% correct, and we are definitely getting 5 multiplied by 10 to the power of 15 hertz. Now, the next question, my dear learners, is to ask ourselves if we have actually answered the question altogether. So, to check if we have answered the question is to say, but the question asked us to identify the type of electromagnetic radiation. It did not say we must just perform a calculation. We must still go back and identify it. So for us to identify it, we then go back to this particular table and we look at the type of radiation. And for the type of radiation, we can see that from 10 to the power of 5 hertz to the power of 10 hertz, we have radio waves. 10 to the power of 10 hertz to 10 to the power of 11, we have microwaves, and so on and so on. Now, we are interested in a frequency that is between 10 to the power of 15 hertz and some way altogether. And our answer there is definitely going to be ultraviolet radiation altogether, because its frequency ranges between 10 to the power of 15 hertz minus 10 to the power of 16 hertz. So our answer there is definitely ultraviolet radiation. Ultraviolet radiation. Altogether. So 1 mark was for the formula, another mark was for the entire substitution, another mark was for the frequency, and the last mark is for identifying the type of radiation altogether. And that is where your 4 marks actually comes from. And then we are required again to state one application of the type of radiation identified in question 8.4.1. So we have correctly identified that the type of radiation is definitely ultraviolet radiation. So we go and we say, okay, what is the one application of ultraviolet radiation that we know? Because we want application, just one application of the type of radiation identified from this question 8.4.1. And definitely, my dear learners, we identified it as ultraviolet radiation. It means then we are required to give one application of ultraviolet radiation. Are we together? Right. Then we definitely know that ultraviolet radiation is used to sterilize. It is used to sterilize medical equipment. And remember what I said to you, the key word there is definitely sterilize. We don't just clean, we sterilize. So we remove or kill all the germs. So it is used to sterilize medical equipment. Another use that you are familiar with is that in banks and even in shops, it is used to detect counterfeit notes. It is used to detect counterfeit notes. Now, what am I talking about when I talk about counterfeit notes? I am talking about notes that are fake. That means money that is not original, the one that is not genuine altogether. So we use it to detect counterfeit bank notes. So when you go to a bank, you know, sometimes they take your money and they put it through that machine underneath, and then they are able to then check if there's any of the notes that are not true notes, meaning any of the notes that are counterfeit, any of the notes that are fake. So it is definitely used for that, to detect counterfeit banknotes. Another one it is that it is used to sterilize medical equipment. Then we go to another question. Now, another question there, it says, different types of electromagnetic radiation have different frequencies. And then this can influence their properties and what each could be used for in our daily lives. We definitely know, my dear learners, that all the different types of electromagnetic radiation, they definitely have different frequencies. And this can influence their properties and what each could be used for in our daily lives. And we know that for sure, my dear learners, that different types of electromagnetic waves, they definitely have different uses altogether. Then we are required to do this in 8.1. Choose the frequency from column B that matches the type of electromagnetic radiation in column A. Write only the letter A to C next to the question number 8.1.1 to 8.1.3 in the answer book. For example, 8.1.4 D. So what we are going to do here is we are going to say, okay, 8.1.1, then we'll have another answer for 8.1.2, and then we'll have another answer for 8.1.3. So if you check there, we are just required to check according to 8.1. We've been given the column A, which is the type of radiation. In column B, we've been given the frequency measured in hertz. So according to this question, we are going to look at column B and look for the frequency that corresponds to the type of radiation that is given there. So I'm going to look at, for example, 8.1.1 and actually tell them which frequency corresponds with that of ultraviolet radiation. And I will do the same for gamma rays as well as for radio waves. Now, the frequencies that are given there, it's 10 to the power of 23 hertz, 10 to the power of 7 hertz, and 10 to the power of 16 hertz. Definitely A is the highest frequency, right? Because the frequency is 10 to the power of 23 hertz. And then when you look at C, you can definitely tell me that C, it's somewhat between B and A. So it's somewhere in the middle. It's somewhere in between the highest frequency and the lowest frequency. And then you look at C, you can definitely see that, I mean, you look at B, you can definitely see that B is 10 to the power of 7 hertz, and that is definitely the lowest frequency. So A is the highest frequency, B is the lowest frequency, and then C, it's somewhere between the lowest frequency and the highest frequency. Then what I only have to do then is to check between all these types of radiation, which one must have the highest frequency. And we know gamma rays have the highest frequency. We know that those with the lowest frequency are definitely radio waves. And then the ultraviolet is going to be somewhere in between. We definitely know this. It's recall work, my dear learners. Gamma rays have the highest frequency of all electromagnetic waves. And the highest frequency, I see that it's 10 to the power of 23 hertz. So the answer there is going to be A. Why am I writing A and not 10 to the power of 23 hertz? Because they said we must only write the letter A to C next to the question number. For example, 8.1.4 D. So for us, 8.1.1 is going to be A, because that's the highest frequency, and the highest frequency we associated with gamma rays. And then in 8.1.2, no. Let's recheck this quickly. Gamma rays are 8.1.2. Gamma rays are 8.1.2, and they are the ones with the highest frequency. So gamma rays, it corresponds to A altogether. We'll come back to 8.1.1. Then radio waves in 8.1.3, they correspond with the lowest frequency of all of them there. And lowest frequency, it's 10 to the power of 7 hertz, which is B. So for radio waves in 8.1.3, it corresponds to the lowest frequency, which is letter number B. And then 8.1.1 is ultraviolet radiation, and it has a frequency that is less than that of gamma rays, but its frequency is higher than that of radio waves. So this ultraviolet radiation, its frequency must be between that of gamma rays and radio waves. And the one that is in between is C altogether, right? 10 to the power of 16 hertz. So under ultraviolet, which is 8.1.1, we have a frequency that is in between those, and that one is represented by the letter C, and that is going to give us 3 marks. Then we are required to write down one use of each of the following types of radiation. My dear learners, you know that this is recall work. Infrared, we know we use it for signaling in remote controls. Altogether, we use it for signaling in remote controls. It is used for signaling in remote controls. And then we have microwaves. Firstly, we know microwaves can be produced by an appliance that we call a microwave oven that we normally use at home. So what do the microwaves do? They are used to heat food. They are definitely used to heat food in microwave ovens. Secondly, microwaves are also used for satellite communication. They are also used for satellite communication. altogether. And that can also be during broadcasting and so on. But definitely 2 uses there, you could have given us any of the 2. So they are used to heat food in microwave ovens, and they're also used for satellite communication. And we know that is normally during broadcasting and other functions that satellites can actually do, but basically that is satellite communication altogether. And that word there, communication, is a keyword. It has to be there. Then another question comes. When doctors need to establish the seriousness of a fracture, a picture is taken of the broken bone. The picture below shows a fracture. So doctors will then examine this picture, my dear learners, to look for fractures in the bone altogether, meaning to look at how broken or how much broken is a bone. So they will take this picture, and this picture is actually what we call a radiograph. It's a picture that can actually show you how the bones are actually looking, if the bones are broken or if the bones are not broken. Then we are required to write down the following. To name the type of radiation used for this procedure. We know when the doctors are examining broken bones, they use an X-ray machine, and the X-ray machine produces X-rays. And those X-rays are able to penetrate through the skin, but they will not penetrate through the bone. And then a picture will then be projected on a screen. Are we clear? And it can even be printed out for proper examination of the bones. So we definitely use an X-ray machine, and that X-ray machine, it gives us radiation in the form of X-rays, and that is 1 mark. Then in 8.3.2, the property of this type of radiation which enables it to perform this procedure. So what property of X-rays does it have, which then allows it to actually give us that picture, to allow us to be able to examine those broken bones? It is because the X-rays are able to penetrate through their skin. Altogether, they are able to penetrate through the skin. So the answer there is going to be its ability to penetrate through the skin. But not through the bones. But not through the bones. So remember that it is because of their ability to penetrate through the skin, but not through the bones altogether. So that is the property that these electromagnetic waves actually have. And we know the reason that they are able to penetrate is because of they have a high frequency and they have a high amount of energy. And because of the high amount of energy and the high frequency, then they are able to penetrate through the skin, but not through the bones. Then, what are the dangers in 8.3.3 of overexposure to this type of radiation? Now, if you are overexposed to this type of radiation, remember, X-rays have a high frequency, they have a high amount of energy, and they penetrate through the skin. So if they penetrate through the skin for a long time, or they are exposed to the skin for a long time, then they are going to cause damage to the skin tissue and the tissue inside the skin. And I'm just making it easy for you there, my dear learners, by just writing everything. So it causes damage to the skin tissue and the tissue that is inside the skin. Just put it like that and you will have your mark. Remember, my dear learners, the fact that it penetrates through the skin, if you expose your skin for a long time to X-rays, then it will penetrate some more and it will cause damage to the skin itself. And secondly, it will cause damage to this tissue that is already inside the skin. So the internal tissues are also going to be damaged. Remember, when you're talking about tissues, we are talking about a group of cells that we are made up of altogether. And then a radio program is transmitted in the FM band on a wavelength of 3 meters. We are now on 8.4. Then we are required to calculate the energy of a photon of the radio wave. So the wavelength there is given as 3 meters, and we are required to calculate the energy that is carried by the photon of this particular radio wave, right? So if we have the wavelength, we know the formula to use is E is equal to hc over wavelength. Now remember, I'm looking for energy, so I will substitute my h, c, as well as the wavelength, and then I will have my answer. So just in the interest of space, let's write 8.4 there. Right, so this is 8.4. So the correct formula to use is E is equal to H multiplied by C divided by the wavelength. I am looking for the energy. We are fine. Do I have the value of H? Yes, we go to our data sheet and we know the value. It's 6,63 multiplied by 10 to the power of negative 34 joules seconds. Altogether, this is the Planck's constant. We get it on the data sheet. C is the speed of electromagnetic waves in a vacuum. We definitely know that the value is 3,0 multiplied by 10 to the power of 8 meters per second. And we know that we are going to get it from our data sheet divided by the wavelength. And the wavelength we've been given as 3, and we are happy because it is given in meters. So I will divide there by 3. And then my final answer, we go to our calculator. It will give us 6.63 multiplied by 10 to the power of negative 34. And that we will multiply by 3,0 multiplied by 10 to the power of 8, right? And we will divide all of that by 3. And the answer that we get is 663 multiplied by 10 to the power of negative 28 joules. Altogether, we double check our answer. 6.63 multiplied by 10 to the power of negative 34. We multiplied that by 3 times 10 to the power of 8. And we divide that by 3. So that will give us 663 multiplied by 10 to the power of -28 joules. So 1 mark for the formula, 1 mark for that substitution there on the numerator, substitution on the denominator, and the final answer with the correct unit, which is joules, a capital letter J. Right, so that brings us to the end of that particular question. Then let us look at the next question. It says some electromagnetic waves are listed below. There they are: UV rays, infrared rays, radio waves, X-rays, and definitely that is gamma rays. Then they tell us, how are electromagnetic waves generated? We definitely know that for us to generate an electromagnetic waves, the charges must accelerate. So we will generate electromagnetic waves by accelerating charges. So we will generate that by accelerating charges. And we know when we accelerate charges, then there is a changing magnetic and electric field that are mutually perpendicular to each other and the direction of propagation of the wave. It is as a result of accelerating charges. All together, that's a mark. Then from the list above, write down the waves used in a TV remote control. We definitely know that it is infrared rays. And remember, they said from the list, so we look at that list. So we say those are infrared waves, rather infrared rays. That's a mark. Used to sterilize instruments in hospitals. We definitely know that we use from that list UV rays. That's a mark. Alternatively, my dear learners, you could have talked about these ones. These are gamma rays. I know you are not used to that. You are used to us actually writing it in full, but just know in future that letter represents the gamma rays, right? So we also know that gamma rays are used for the same purpose, to sterilize medical equipment altogether. So remember that, my dear learners, any of these two is correct, your UV rays or your gamma rays. And then we want those with the greatest penetrating ability. Remember, those that will have the greatest penetrating ability means we are looking at those that carry the highest amount of energy, because the amount of energy has to do with how much or the ability of that particular electromagnetic wave to actually penetrate. And as a result, we know that those that will have the highest penetrating ability are the ones that will have the highest amount of energy. And we definitely know that those are gamma rays. Altogether, those are gamma rays, these ones there. Right, they have the greatest penetrating ability because they have the highest amount of energy. And how did you know that they have the highest amount of energy? Is because you know that gamma rays have the highest frequency of all electromagnetic waves. Then we are also asked to give from this list those waves that are used in the treatment of cancer. And still, my dear learners, we know those are gamma rays. Gamma rays are the ones that are used to treat cancerous cells. All together, right? Then in 9.3, we are being told ultrasound is used to obtain an image of an unborn baby. So they use ultrasound to get an image of an unborn baby. Then we are required to briefly explain why X-rays cannot be used for the same purpose. So why do we prefer to use ultrasound? For example, when a mother is going for a sonar to actually check if the baby is healthy, the movement of the baby, and all those things that gynecologists will check. They use ultrasound and they do not use X-rays. Why don't they use X-rays? It is because X-rays have a high frequency X-rays have a high frequency and therefore high energy. And can penetrate the skin, right? So X-rays have a high frequency and therefore they will have a high amount of energy and they can penetrate the skin, resulting in tissue damage of the baby. And that will result in tissue damage of the baby. Altogether. So we really cannot use X-rays because to actually examine the baby, you know, to get an image of the baby, because they have a high frequency and therefore they will have a high amount of energy. And because of that, they can penetrate the skin and that can actually result in tissue damage of the baby. It means they can damage the organs of the baby, the cells of the baby, and so on. So we don't want that. That is why we'd rather use ultrasound, but not use X-rays. And then in 9.4, they tell us an X-ray photon incident on a body has a wavelength of 2,1 times 10 to the negative 9 meters. Calculate how much energy the photon imparts on the body. Right. So basically, we've been given the wavelength of the photon that is incident on a body, and we want to know how much energy then the photon imparts on the body. Right. For the sake of space, I will write 9.4 there